Hello guys, here I am again, Gilberto Thomas from Brazil, and today I'm going to present some extra and very useful tools that CompuCell brings to you. And as usual, I must remind you that this lecture is being recorded, live streamed, and will be distributed to YouTube. Okay? Okay, let's start. Here is the topics that I'm going to talk about today. There is a special feature in CompuCell that allows you to describe fields. But what is a field? This is the first thing we are going to introduce today. We are going to talk a little bit about types of the fields, give you some examples, and show you how to represent the scalar and vector fields. And at the end, we are going to implement the scalar and vector fields in some simulations of CompuCell3D. Okay. After that, I will show you some new tools that are very important. That is one of those is the AdhesionFlex plugin. The AdhesionFlex plugin deals with difference between cell adhesion molecules on the surface of different types of the cell. And of not only different types of the cell, but different types of molecules. A cell can have more than one kind of adhesion molecule, and they behave differently one of another. So you have this adhesion, this plugin to take into account those possibilities. To start, I will talk briefly about the catenames from the molecules, types of molecules that can be presented on the cell surface. And with the plugin, I will give you an exercise where we are going to use this plugin, a cell sorting experiment. Finally, two things that is sometimes important in CompuCell is how to make movies from the CC3D data you are getting from the code, from the simulation, and how to save this data in an external file to be used after for whatever you want. Okay, let's go. For example, field. What's a field in physics? As usual, field is a concept to describe the space or a region of the space which presents an alteration or a deformation created by a physical quantity which is present in it, and its variation on time. Here are a few examples. Gravity. See, there is a field that's acting over the ball that makes the pendulum oscillate. Here, there is another field that makes the block, the cube, levitate, the magnetic or diamagnetic field. And finally, here in this last animation or movie, we have a candle. Well, what is the field? Well, if you approach your hand near the flame, you feel something, the heat. The heat is a field. Both fields are different. We have scalar fields and we have vector fields. This kind of fields, for example, here I have a picture to exemplify a scalar field. We have the sun, which is the biggest flame we have around. And on the other side, we have a South American map with color codes, color regions represented the temperatures of the regions. So a scalar field describes the space with a single number, a scalar. So I can say that in this point of the map, the temperature is such that this kind of the map, the temperature is another one. And that's it. You can understand perfectly the how things are in Brazil, for example. The weather in Brazil is like that, hot. Okay? This is an example of a scalar field, only a number to describe. The other field we have studied that is a scalar field. We didn't use these words at that time, is the pressure that the cell is suffering in that simulation we did 2 years ago. Okay, but we have another kind of field, the vector field. It's a more sophisticated one where the space is each point of the space is described not only by a number, but also with oriented direction. And here is the example. We have the Earth. The Earth produces the gravitational field, and this gravitational field has a vector at each point around it, around the Earth. The last picture at the right represents a more correct representation for the field. The field is radial, directed towards the Earth in each point of the space. This is why objects fall. If you are in a very small region of the space, like this person here, you can consider, due to the great curvature of the Earth, that the surface is flat. The Earth is not flat, okay? But then you can, in a good approximation, consider that the field here is parallel lines oriented towards the ground. Okay, but anyway, you need a vector to represent each point of the space, different from the scalar field. There is another example I can show you. See here, clouds moving around. They have each agglomerate of clouds have some speed. And we can represent the motion of these clouds through a field, the velocity field, like here. If you look here, you can get quite sure that how the winds are how the air is in motion in each region of this graph, because of we have these small vectors here showing how the wind is in movement. So it's an example of a scalar field, a vector field, and it is the velocity field. And this is the field which we are going to be interested in this particular lecture. Okay. Note that there is a small difference between the gravitational field, for example, and the velocity field here, because the gravitational field needs the mass, for example, the Earth mass, to produce the deformation of the space. The velocity field show how the participants of a physical system, for example, the clouds, flow in this space due some external force. Okay? So let's move on. Here are another examples. We have this first one. It's I will get rid of the sound. Flock of birds moving together. See, I don't know if it's birds or if they are bats, starlings. They say, okay, it's birds. Here we have a flock of ships moving. You can associate to each ship a vector and represent the whole flock through a set of arrows, for example. And finally, we have, for example, the flow of a liquid of something inside a pipe. See? See? Inside a pipe, you can describe the field, the velocity field, like this. The molecules of the fluid which are close to the walls of the tube, the channel, practically doesn't move because they are attached to the walls. The ones which are in the middle have more velocity, more speed. So you have a profile. Well, it's not. Mhm. You have a profile like that. It's like a parabola describing how the fluid flows inside the tube. Okay, so it's very useful to understand the velocity field because we can use it for cells. At the left, you have a tissue in movement, see? And then the right, you have, for example, cell migrated to close a wound, for example. With time, this empty space here will be uh, filled with the cells. In the question is how to implement the description of these movements in in simulations. How to be can you use the velocity field for cell movement? Okay, that's what we are going to understand. Try to understand now, and this is the where the extra fields plays the role in the CC3D. The velocity field helps you to visualize the evolution of the system of the individual participants of the system. You can keep track for each one of the objects in your system. You assign to each one a vector and follow that vector. Um, this is an expression steppable in CompuCell. You can see how it works in the manual. Here is the copy of the manual, how to add to manage the extra fields for visualization purposes in the simulation, but we are going to do this here. The thing is, the extra fields are not in the simulation wizard. We have to do them to include in the simulation by hand. Not completely by hand, but not from the wizard. Let's see how we do that. This is made from the into edit. When you have your simulation finished, I mean, you created the simulation, finish the simulation, introduce everything you want from the wizard, finish the simulation, then you have to implement the extra fields, to include the extra fields. Okay? This is done from the Python CC3D drop-down menu. There is an entry here called extra fields, and these extra fields possibilities, we have see 8 different options here for scalar fields and 8 for vector fields. For each one of the possibilities to scalar and for vector, we have two sub-options, let's say that. You can implement these fields as a cell level or a pixel level. What does that mean? Means that if you introduce the scalar fields as a cell level, we are going to follow the center of mass of the cell. If you introduce the scalar field at pixel level, we are going to follow each pixel of the cell. Okay, it depends upon what you want to do in the simulation. You have those two choices. And the same for the vector field, cell level and pixel level. And here there is a possibilities to include in the start function, in the step function, creating the niche. So we are going to see now. Okay. Let's see then how to implement it. Now I'm going to ask you to download from the menu, from the student materials demo code, the exercise 431, which has that. And let's do, since the exercise is too long to code it again, let's use one we already used 2 days ago. That one with contact inhibit role, when we have two windows keeping track of the target's pressure and target volume for the cells and the pressure of the cells. We are going to use this example, this exercise, to add now the extra fields. Okay? Well, let's give you a minute to download and open to edit the code, the downloaded code, and then we are going to analyze it. It's easier this way now. Yes, E531_2026, something like that. Okay, I think you have it. If you need more time, please tell me. See, the procedure is the following. If you are going to start from the 233, you would have to do that. Okay. First, you would load the 233 example again with a new name to not mix with the old one. Okay. Save project as. Okay. This is the if I didn't have given you the code, you would do this way. Then you would go to the CC3D Python tab, and in the last line of the drop-down menu, there is the Add Steppable command instruction. When you click this Add Steppable, you have two things happen. First, a window open, and you have to give a name for this new steppable you are including. The code I give you already has this. You can follow what is in the steppable file. I put the name extra field visual steppable. Okay. This click OK, and the modifications occurs. First of those is that in the main Python file, it's added a new entry for the new created steppable. Here is the wrong name because it's an old slide. Anyway, you should have this name here in your main Python file, the extra field visual. Okay? The second thing is it also includes two blocks in the steppable file, which is the creation of the field itself in this line here, and which is in green. You have to give the name of the field you wanted to describe. When you use the wizard, the drop-down menu, actually, only one entry is added when you add the steppable. But we are going to need two entries. One for pressure, one for volume. Okay, and both are scalar fields. So you, as you see in the code that I gave you, you have two lines. I think it's 104, 105, one for pressure and the other for volume. The second block that the add steppable creates is this one in orange here, okay, which is the place where you have to this is if you want to include by hand by drop-down menu, you are going to use that option in the extra fields of the drop-down menu. And this is, as you can see in the code I gave you, in the init function. This is the part of the steppable that initialize things. For example, the fields. Okay? So let's move. We have now the fields created by self-created scalar field, blah, 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 pressure and volume. And we have to define now the placeholders for the fields itself. Here, I created here two variables, field P and field V, and attribute to these variables the fields. Self-field pressure, self-field volume. See, I have to use here the same names that I have used when I created the field. Here to here. Okay? And the next step in this steppable is the loop where you fill the placeholder. I mean, you complete the field with the values they have. So for the field P, we are going to say that each cell has its own pressure. And for the field V, each cell has its own cell volume. So we built this way both fields, the pressure field and the volume field. Okay, let's go. So now you can run the code if you haven't done yet. You should, when you code, if you start with one step, you have this window here, because I already give you with the 5 windows open. If you had started with the old code, the cell pressure one, that one didn't have this extra windows here for volume pressure. And you have to go to the window menu, drop-down menu, and new graphical windows, and choose for each one volume and pressure, and that's it. Then you can use tile function here to arrange the windows in your simulation space, in your player. Right? So after running, you should have something like that. Put it to run now with non-stop. And what you see is that the cells at the right windows, the volume and the pressure, have color code indicating each cell pressure and each cell volume. So I can say the red cell in the bottom right window, this one, is the one which has the bigger volume. And in the above, the window above, the red ones are, sorry, this is the biggest volumes. And here is the biggest pressure. See, 8, 7, and 50. The red ones are about to divide in this picture here. And if you continue your simulation to the saturation phase, you will see that the cells reach more or less the same color because it saturates everything. If whoever got the saturation phase, please put a snapshot in the chat just to check. I'm running the simulation right away here. I can show you here. Just oops, I have to tile again. See, the saturation was the space is completely full, and the pressure starts to saturate. The target volume starts to constant value, and here we have pressure with. I think I have to do that to update the screen. See, the cells are pretty much green here in the pressure. Here I also have to, and most of the cells are in the middle region of the color bar. So they are stabilizing. The ones which are red is because they were already big when the saturation started, so they kept that values. Okay, good. Let me go back to the class. So let's continue. So with those fields, those are scalar fields. Just a value, a number to describe the cell properties. Okay? The cell state, let's say that way, in volume and in pressure. Now, let's do the following. This morning, Julio presented you an exercise based on the one I showed also 2 days ago, where it has multiple cells dividing and moving around. Okay? And with a new approximated model, the compartmental cells, which make the cells knows who is who. That they don't have to attach to each other. Well, you can do that. If you want to make a tissue, you can modify the energies and make the cells stick together, but still they will maintain its own identity, even stick it together in a tissue, okay? So let's use this Julio exercise. This again is the exercise 532 underscore 2026 in the student materials. Please load it in the to edit. Then let's go there. I will change the screen to open the file. See, this is the file you have there. Now, I have to make some small changes in Julius simulation code, change a little bit the cell lambda volume for the nucleus compartment, and I have limited here in line 53 the number of generated new cells, just to not have the space completely full, not full the grid. Okay. If you need more time, please again tell me. Those are the basis changes. Let's go to the. Here I will repeat only to show you how to implement the extra fields again. We have to go to the drop-down menu of Python code, Python to edit CC3D Python drop-down menu. Add the fields, but now the field must be a vector because we want to describe the cell speed, the velocity of the cells, how kind of motion they are doing that. Huh? So remember again, as we did before, to deal with velocity, we need position of the cell at two different instants of the time. We did that in last 2 days ago when I defined the velocity, the speed, calculated the speed against the lambda vector. Okay, we are doing the same thing here. We needed to add dictionaries for the old position of the cell. And in particular, we are going to keep track of the position of the nucleus part of the cell, the compartments of the cell nucleus, only of the nucleus, because it's the biggest part of the cell, so the heaviest, let's say. And we introduce now, using the drop-down menu again, self-vector field velocity this time. We introduce also the placeholder here, the field, as we did for the pressure and the volume before. And do we have that small routine to calculate the displacement? And remember, we have to take care with if the cell cross the border. So we have that this correction here to take that into account. For delta, it was displaced here. The green box should be a little bit to the bottom here to include the lines 107 to 110. Okay, those are the subroutine you already know from before. And we calculate the cell velocity this way, velocity x, velocity y, and we fill here. See, my boxes are wrong here, sorry. We fill the field with components. We don't need to calculate as before the intensity of the intensity of the velocity. We are going to put in the vector field the components of the velocity. N val x component x of the velocity, n val y component of the velocity. So we fill the field now with a vector. Since we are in 2 dimensions, the z component is always 0. But you have to put it here. Okay? And we updated the old dictionary with the actual one to do the loop, and had always 2 values, the value now and the value old, to calculate the delta, how much the cell has moved in that time interval. Yeah? Okay. Put it to run now. You have, can you explain the conditions in the green box? Yes, I can. Let me go back. The conditions in the green box is the condition to avoid jumps in the delta x. Remember, for example, if a cell is in position x equals 200, and your grid has 200. So it's at the border of the lattice. And in the next step, the cell goes to the right and appears at position x equals to 1. If I just do the calculation as it is in line 72, the delta x would be 1 minus 200. But that is not true, because the cell only moves from 200 to 0 to 1, only 2 space, 2 pixels. Then I have to correct this problem when we cross this border. Okay? This is done for the x and for the y components. Okay, let's move on. So if you run down the simulation, you have this image sometime. See, there is it occurs some bugs in the cell division. Let me put it to run here in my computer. I will put it here just to see the cells are divided. See, sometimes occurs this problem. This is because, you have to refine a little bit your energies. See, the nucleus here was lost. It belongs to this cell here. This lamellipodium escaped from where? Where is the cell without lamellipodium? Here in the middle. Eventually, the lamellipodium will find its owner here. If the cell touches there, it will attach again. Oh, almost. See? And in the left, you have the vector fields. Each arrow like that, its cone like that, it stands for for a cell. And the color stands for the value of the speed of each cell. The code itself calculates. Let's see if I can open this. No. We can add. I didn't think it's very useful now. We can put aside of this window a color bar here, standing for the colors, the values of the speed according with the colors. Okay. See, despite the cells seems to be moving fast, since we are dealing only with keeping track of the nucleus, it seems that the cell is not moving so fast, because the cell can change direction, but the nucleus have some inertia to move. So it oscillates around some equilibrium position, only changing the orientation. But some of them really moves, like this one with the border here. You can see. I think that the lost lamellipod found itself. It's not alone anymore. Okay, let me go back. Everybody got this image? Please put some snapshots in the chat. Good, nice. Also you can. I forgot to tell about that. You can change the size of the cones. Here, you come to the tools, configuration, fields. And here you can alter, you can change the length of the cone. For example, it is in 5 here. You can change it just to exaggerate here to 10. See, it's much bigger now. So everything is configurable if you want. Okay? So let's move on. I don't know why it's not. Oh, yes, it was here showing the cell mean and max value for each speed in the window, for the whole speed in the window. Okay, let's continue. Okay, now a very fancy one when we are going to include two different fields, one scalar and one vector. I'm going to use the exercise that I didn't show last time. I left you as a homework or to see. Was the exercise 414 from 2 days ago, yesterday. Um, and I renamed it now to use as a 533 underscore 2026 in the materials. Please download it. And I will explain it in details. Okay. What does the exercise, while you are downloading and opening, I will explain the simulation. The
Gilberto, there was
simulation.
a question in the chat.
Ah,
There was a question in the chat.
okay.
One is, how do I save the values of the velocity field in the CSV, which you're going to cover, I think. And the other one of which is, does the magnitude of the arrows change?
No, I change it by hand here. What changes, the color changes representing the cell speed, but the magnitude, the length of the arrow doesn't change. What measures the speed is the color. Okay, so come back here. What the simulation shows you is a channel here in this picture with a constriction and an obstacle here, the yellow circle here. So the cells start from the left side and they are being forced to go to the right, cross its constriction and avoid the obstacle. It's a flow inside a channel with a constriction and obstacle. Okay, should have it open now. Let's understand what is in the code. So I give you the code already done, ready to run. But we could, if I started from the beginning, I would do this way. Again, from the drop-down menu, I would create the initial field here in this init function. And I have to include also the old positions, because again, since you are describing velocity, we always need to positions at two different instances of time. So I have to keep track of the old one. Okay? So I have two fields now. Self-vector field, scalar one, actually vector one, velocity, and the scalar field pressure. Why? Because we are going to keep track of the velocity and the pressure inside the channel for each cell, while they are flowing into the constriction and encountering the obstacle on the other side. Okay? So again, everything as before for the calculation of speed and velocity. We have update here the new cell. Why? Because at the channel, cells are being created. Here in line 37, 38, I'm creating cells where, let me go back to the previous slide. Here, see, at the beginning there are 4 layers of cells. Since the cells are forced to move there, it will be open space here. At this empty space, I will create new cells. It's like if you have a reservoir of cells at the left of the y0 axis. So when the cell moves from there, another one appears. And this appearance must be done by creating new cells at this position here, at this block. Understood? If you have doubts, please let me know. Understand? The cells are moving right. When the cells moving right, empty space appears at the very left end. At this empty space, I create new cells to continue the flux. When the cells reach the right end, I delete the cell. It's like a sink of cells. So I have a source of cells at left and a sink of cells at right. Okay? There is no periodic boundary conditions in this situation. Okay, so when I create a new cell, I have to create also the old positions for the center of mass of this new cell. Moving on. Okay. Updating the fields. Here are the placeholders for the fields as before. Field S is the pressure field, field V is the velocity field. It's here. Now I have to fill the fields. again, I calculate the speed component, the velocity components here, and I fill the velocity field with the velocity components as before, and I fill the scalar field with pressure field. So now both fields are ready to be seen. This velocity field is representing the velocity of each cell, and the scalar field representing the pressure of each cell. And I updated the dictionaries to do the loop for the next calculation. So you can run the code and see what you get. Oh yes, we have some nice pictures there. In the chat. Well, the pressure changed so fast because I'm telling you to change fast. Now it depends. The evolution of the simulation depends on how fast you update your fields. If you update at any Monte Carlo step or each 100 Monte Carlo step or 1,000 Monte Carlo step, you have different evolution. And the update would be very, very different. Yes, because it flickers, because the change is fast. You can play around with this code after to see if you change this, but change the things. But it's very interesting to note here is this, for example, this picture here. See, when the cell crosses the constriction, the speeds increase. This is a continuity equation, isn't it? If you decrease the area, you increase the speed. It's like a hose with water. If you contract, squeeze where the water is going out, the water will go out faster because the area available has decreased, but the amount of mass that is coming is still the same. So the speed has to increase. And you can see this now. If you have only these images, the simulation image, and you can everything is hidden. You can see anything. The same is here. When the crosses the constriction, the cells start to accumulate a little bit here because of the obstacle you have in front of it. And they again are under bigger pressure. So this kind of thing is very useful to see what you cannot see from here. Okay? Okay, well, we go ahead. This is a very cool exercise. I like this very much. And sorry I could not present it on yesterday. But anyway, it's there to you to play. Let's see how I am, where I am here. Okay, so I did that already. So this is the image you have gotten. I already showed that. I will pass. Now, let's change the subject now. Let's go to the AdhesionFlex plugin. We have time yet. So the question is, what are the cell adhesion molecules? What are the types, the plugin, exercise, and questionnaire? Let's go. Answering. In CompuCell3D so far, when we talked about cell adhesion, we are generalizing very complicated, intricate mechanism among cells and the environment. And these mechanisms are very complicated. For example, here we have the interactions between two cells, the tight junctions, adherent junction, lots of biological terms here. And you have the cell extracellular junctions here at the bottom. And for each one of these junction here, we have one kind of molecule, and they are very different from each other. Okay. We can cite, for example, or call these molecules as chems. If you go to bibliography, every time you talk about cell adhesion molecules, they are abbreviated by CAM, okay, or CAM. And there is a lot of them, a lot of families like that. I will not describe this thing because I'm not a biologist. I'm a physicist, but I know them. So you have many families, integrins, IGSF, chems, selectins, caderins, each one with particular, very specific roles in the body, in the organism. And when we are dealing with cell adhesion, we are transforming everything here in only one thing, the J's in the contact plugin. This is a very oversimplified approximation. So you can try to be more realistic now and include a way to make some difference among chems on the surface of the cells. And not only by the kind of the type of the family of the molecule, but also with the amount that receptors and junctions that exist over the cell surface. This must be taken into account, and this is what the AdhesionFlex plugin wants to correct, help. So we have the contact plugin, in the manual, in the reference manual, CompuCell Config manual, you can go there. There is no difference between camps. But now we have this in the entry in the manual, the AdhesionFlex plugin. Let's see more in details this expression here, which regulates the energy in the simulation. See, remember, when we use the contact plugin, we have only to define the energies between pairs of cells. But this is kind of complicated because it has kind of problems. Because, if you have many types of cells, the number of J's increases n squared. So you have lots of parameters to adjust. Okay? Another thing, as I said before, we have in biology the adhesion depends on specific receptors between pairs of cells or between cells and extracellular matrix. Caderins act among the cells, integrins between cells and extracellular matrix in the environment. Huh? So if you have two cells that differ only by number of the cells adhesion molecules, with the contact plugin, we cannot take into account that. There is no way to say, oh, this cell has more junctions, more molecules per surface area than that other one. No, it's everything the same. Okay? And now we have to correct that using this expression. See, the square, the red square here, is the J now. But we are entering how J is built. J now is built from a function which take into account this K here, which is the affinity between two molecules. Suppose that we have two cells with molecules, different molecules, number of molecules are different, and they have some affinity. They like or dislike each other, for example. Okay? And this is represented by the K. F is a function of the concentration of adhesion molecules on the surface of the cells. I and J is the position, is the ID of each cell. Okay, so this square, the red square, is the old J in the contact energy. We are building the new J in this way. Understood? Any questions? So we take a cell. For each cell, we run over each part of cell. We run over for cell I and J neighbors. We run over the concentration of the cell with each one of these neighbors and calculate the final J to that cell. Well, let's go on. So the question should be, remember the J in the contact energy doesn't have this sign, this negative sign here. Why does it have here? Well, this is quite easy to understand. See? Remember, the J it's pretty much the same. See, this red square is the J here. The contact is that. If you want to cell to attach more to each other, to another one, you make J smaller. The lower positive J means a strong adhesion. Okay? So now let's interpret the minus sign. In this plugin, one of the ways to calculate the function f here is that the formula should be, for example, the minimum of molecule 1 and molecule 2. Okay, you take n, m, and n. So you say, well, and attach with the strength of the one which has the less small amount of concentration per surface. Yeah, because, if one cell has 5 junctions and the other has 10 junctions, only 5 will attach. So it's reasonable that you choose the minimum of the two values to produce the final adhesion. Okay? So, continuing. So minimum is the way to calculate F. And this produces a positive number because it's a concentration. So 5, for example. And it gives you the degree of binding of the two molecules. But if you want to have a strong binding, you need a bigger number. But a big number would increase the energy unless you use the negative sign. Understood? So let's make a chain here to say the plugin actually the internally the plugin does the following. It takes the negative of this expression here, and with this negative here and here, they compensate each other. So the final dynamics is high molecular match, high binding, negative energy adhesion negative. It's more favorable, and the cells stick. Okay, let's go. Now let's go to the exercise 534. You have to download it. So again, you can, this one I think you can start it. It's quite easy, but anyway, let's go. We are going to build a simulation with two kinds of cells, a dark and light. It's a cell sorting simulation, okay? But now built not with the contact plugin, but with the AdhesionFlex plugin. So your simulation must include AdhesionFlex, volume-flex, surface-flex, and center of mass. And we are going to use two molecules, Chem1 and Chem2 only, and no integrins, which means that we will not have any kind of interaction between cells and medium. Remember, integrins are the molecules to interact with extracellular matrix. We don't want any interaction. So let's use only cell-cell adhesion, Chem1 and Chem2. So when you are building the wizard, at some point you will be faced with this window here, which is the simulation wizard window for the AdhesionFlex player. So how does it work? See the first line here, which the first arrow, right arrow, you name the molecule. Chem, type here Chem1, and add. Type Chem2 and add. So both will appear in this first left window here, adhesion molecule, and with some interaction here by default. 1 between dark and light cells. And also there is the adhesion interaction matrix, the binding parameters. I mean, remember the K on the formula? Those are here. Adhesion interaction matrix binding parameters. The case. After that, you go to this, you have this window to the left here, where there is a binding formula you can use for each interaction among the molecules. So in these binding formulas here, you have some radio marks here. You can choose average molecule 1, molecule 2, max molecule 1, molecule 2, mean of molecule, and product of both concentrations. In this simulation we are going to choose the minimum of molecule 1 and molecule 2. So you configure these windows, and that's after finish your wizard, you should have this a window like that for your XML, where I read adjust the parameters to have, because remember here it comes with some default settings from the wizard. You have to adjust everything, and this takes time. You have to run the simulation, try, error, and so I did it for you and put here the reasonable values to get the simulation running okay. So your code must have for the density 6.1, 4.1, 2.1, and 3.1. Look, each cell has two molecules. Cell D has Chem1, cell D has Chem2. Cell L has Chem1, cell L has Chem2. And the evolution, the dynamics will deal with these molecules according with the formula, which is in the line 53 here, the minimum, molecule 1, molecule 2. And here I have adjusted also the binding factors to be like this. Chem1, Chem1.25, 1 with 2.5, and 2 with 2.25. So start the code, but at the beginning run with steps, not with the run button. Let's see what you have. Yes, this is a very, very, very usual sorting, but achieved with the AdhesionFlex. Okay, then this is another alternative way to build your simulations if you want to. I remember some people asked about two different molecules during the workshop, and then you have your answer now. Of course, you have to refine a little bit more the parameters to have it more smooth, more fancy, but it works. Okay. Okay. Two final interesting things. How to make movies with CompuCell. Yes, nice rectangles. Yeah, it's not very nice. It should be more rounded. That's okay. Thank you for the nice. Okay, this how to make moves. Okay, when you are running a simulation, eventually you want to, as I have shown sometimes here, movies from the results I have gotten from my data. Okay, and one way to do that is to save where am I? To save the images. But before to save your images from the simulation, you have to say CompuCell to to prepare, let's say, uh, uh, to prepare the engine to have the simulations, or the image organized in a sense that you could read some file and produce a movie. Okay? And this is done from this small photograph icon machine you have on the top of your graphics window here. When you put the cursor over it, is take a screenshot. Okay? So this is, when you click that, something new is created in your simulation folder. But before that, let's see. Then, after you click that, you have to go to the configuration file here in the tools and say to the CompuCell to save images at every amount of Monte Carlo step. For example, this image you have in the screen is 100, but you can have 1,000 to 50, I don't know, whatever. And you also can change the resolution of the image. But remember, this occupies lots of space depending on the resolution. Okay? After that, when you run the simulation, what occurs in your workspace is that you have these two new folders. The cell field 2D X, Y, 0. What does that mean? Means that when you click here in the take the screenshot, your layer showed in the screen is the layer 0, which you can see here in the XY small window. Of course, if you are in 2D, doesn't make any difference to this value. But if you are running a 3D simulation, for example, and if you want to save images for a specific layer inside the cell, you can change this layer here to the layer you want, for the number you want. So this number will appear in the name of the folder, this one, from 0 to whatever. And you have here another folder, which is screenshot data. This is where the information about the images which are being created are. Okay? So you have these two new folders, and what is inside of it is this. Inside the folder, you have the images being saved at amount of Monte Carlo's interval of Monte Carlo steps you choose. In particular, this one is each 500 Monte Carlo steps. Okay? Then you have all images for your simulation. Now you are ready to make the movie. It's very fast. So after the simulation ends, you open the configuration file again and go to the same screenshot movies tab, and go to the create a movie now. When you click in that green button or blue button, a second file manager windows open, and you select the folder where your simulation saved that data, that information. Usually is in your CC3D workspace folder in the users file of Windows. Remember? Let me show here where. Here. See, this PC, it's inside. You have the users file here. Inside your user, you have CC3D workspace. Every single time I click play in my player, it stores something here. So you have to keep track that this takes a lot of space and is from time to time you have to go there and clean it if you don't need that much of information. So here is the folder. You have the files with the images saved. Okay. So you select the folder then, and when you select the folder, it will identify that inside that folder you have that subfolder with the images and the screenshot information, and he will build them for you. And this message will appear in your tab, screenshot tab. See, at the beginning there is no information about the movie. Now it has. Movie successfully made. And a new subfolder in the simulation folder with the movie subfolder called movies is created here. Okay? Then you can continue in the same tab, screenshot movies, and show movie in the file browser. You click there. The file browser will open the subfolder movies and show you the movie that is inside. You click in it, double click in it, it will open. And you have your movie done. Okay, it's quite easy to do that. I'm not take too much time. It's straightforward how to do the moves. Okay. And then I have time for one more thing, which is also very important. Oh, yes, it seems that, okay, you have to configure because I was using an old code to make the presentation, I forgot to update the 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 place where FFmpeg is. So you go to the CompuCell installation. Actually, let me put it back here, the simulation. Let's see. When you open the tools here and go to the Make Movies, it's set up here. The first tab of setup, you have to search for the FFmpeg executable applicative. So you reconfigure I forgot that. Thank you. So you have to configure here to say, well, the FFmpeg, that is the code to make movies, is in such a place. You have to go there and search. See, it's in the wrong place here because it's an old version of the CompuCell. You have to search in CompuCell's 4.9. Probably now is not mini conda 3, but 3 is mini forge, and search for here. Search for it here. For example, FFmpeg, see, somewhere in here must have the, you're going to find it there. Okay? It's highly configurable, so it's easy to, here it is. See, it's in the folder, CC3D environment, blah, 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 blah. Then you choose this one. And see, he configures the player, again. Okay? Okay, let's go back to presentation. And now, one thing that is very important, somebody just asked about that, how to save data in CompuCell. That's the way. You have to create output files, of course. And there is no plugin, nor drop-down menu for that yet. So you have to do that by hand. The code I give you is 534W, W for writing, is already ready to print data, to save data, actually. Well, how do you do it? For example, here is the code. You download the code, open there, and you have this. Let's say if you want, for example, to keep track of the volume and the surface of a specific cell, to see what's going on with that cell. So I choose it, cell ID 40. This is the cell that I want to follow. The next step is to create the folder for where the output files will be saved. CompuCell by default have a inner function which is self-output dir, where it's defined when if you doesn't change is inside your CC3D workspace in your user file, user space, the one we just saw. Okay, you can change that. You can change the output dir. But for now, it's the default file. This is the file, the place where you define it at the first page of the wizard when you give the simulation name. The second line is choose a place for your simulation. If you change the workspace, then that new one will be the output dir. Okay? So here I am changing the file name. I'm creating a new file name here, a file path, actually. See? I am attaching or concatenating the output dir, which is in the variable dir here, with the cell ID. I mean, I'm putting the word cell ID in the name of the file. I'm summing the number of the cell ID, which is string. I'm transforming in string the number 40 here. And I'm giving some new information for the simulation. For example, Grid size. What is the size of my grid? For example, if you wanted to make many different simulations to change some grid size, so I know that this particular simulation that I'm saving have the grid size that I defined on the XML file, which is in the variable self-dim x. Okay, this creates then the name of the file. And I update this number adding the extension celldata.dat. So this line 17 creates the full file name with the path for the output file. The line 18, I open the data, the file, sorry. I am open the file, see, open for write, and I am creating a header for the contents of the file. At the very first line, time, cell surface, cell volume. This is written in one line. And I close the file to save it. Because, if you don't open and close your file every time you write something inside, you may lose everything in it. Because of the Windows or the system tries to keep buffering everything and dump from times to times. If something happens during the buffering, you lose everything. So open and close. Open, write, and close. Open, write, and close. It takes a little bit more time for computational time, but it's safer for your data. Okay? So this is done then in the start function, defining the destination of the data I want to save. In the step function, I'll save the data. So I run over the cell list and search for the cell ID that I want, that is number 40, and when I find it, I open the data file, and I write in the data file MCS as time, cell surface, and cell volume, and close again. Okay, this will be done every Monte Carlo step, or every interval of Monte Carlo steps you want. So this is going to save you a text file with 3 columns. Each column represents one of those quantities stored here, MCS, surface, and volume. Understood? Okay, so is there a way to save simulations? Yes, but it's a bit different thing. You can search in the let me just answer to you, Maisha, here in the tools configuration. I think it's here. Here. No, here. Use this to replay. No, not here. I don't remember what it is. It's a new feature. Here. In output, restart. If your simulation crashes during the running, if you habilitate this window here, it keeps saving some states of your of your simulation from times to times, and then you can restart later from the last state you have saved. But you have to habilitate this option here. Okay? I think you should, the manual, you have explanation. So where am I? Okay, so right here is the way the code says. Remember, I put cell ID as a text, number 40, the cell I want to watch, the grid size 100 as defined in the XML, and the extension cell data.dat. And it's saved there in the CC3D workspace in your users file, system users file. Okay? It's quite easy. And that's what how the file looks like. You have the 3 columns, you have time, surface, and volume, and the and the evolution with time. Then you can use this for plotting, for analyzing, for anything. Okay? Okay, with this, I conclude my last talk. I hope it has been useful for you.